Today, you're going to hear a little bit about ArcticDB, and you're going to hear from the developer itself. Please welcome Vasil Pashov.
Yeah, hello all, and thank you for coming to hear about ArcticDB. I will talk today about Arctic and one other project which is complementary to how we use Arctic at Man Group. Just before talking about Arctic, I wanted to share a bit about Man Group, and so that you know how did Arctic come to life, and how do we use it, and how do other people can use it. So Man is an active investment management firm, which in layman terms would mean a hedge fund. So we have 5 hedge funds, and we do trade on every major stock exchange there is in the world. We do have about $160 billion assets under management, and we do trade them daily. We don't do high-frequency trading, but we do intraday trading and daily trading. And Man is with headquarters in London, and it was founded about 200 years ago. We are also traded on the London Stock Exchange, which makes us heavily regulated hedge fund. Now we do have tech offices all over the world. In UK is the largest one. There is one in the USA, and there is an office in Bulgaria. So we do everything from start to finish in Bulgaria as well. And we are hiring. The office is new. We have about 20 open positions. So if you want to learn more about what we do at Man and how we do it, you can check with us at the booth outside. Now, the hedge funds that we have, as I said, there are 6 of them. We do all kinds of trading. We do have fully automated trading with algorithms, which trade without human interaction, but we do have also discretionary trading. And even the discretionary trading and portfolio management needs to have some kind of technology behind it, because the data is too much and people nowadays cannot take the right decisions without the help of technology. And at the heart of every hedge fund, Man Group included, is the quantitative finance. So the idea behind quantitative finance is to generate risk-adjusted alphas. And that might sound scary, but here's the idea. An alpha is how better are you performing than the market. So let's say you have some money, and you have decided to spread them evenly across the 500 biggest USA companies, also known as the S&P 500 fund. On average, you would get about 7% return on investment. But let's say you're smart and you think that you can pick 20 stocks which are winners. And you do this and you get, I don't know, 20% return on investment. Then you have an alpha, you have a positive alpha. And our goal is to get alphas to be better than the market. And the risk adjusted means that we want to do it safely. We don't want to do high risk operations, because among all, some of our clients are pension funds, so we don't want to blow our clients' money on high risk investments. And how do we do it? We do it with mathematical models. There are one of the brightest people that I've seen work at Man. And there is all kind of maths. There is statistics, Monte Carlo chains. Some people do PD, some people do AI, some people do algebra, time series, like whatever you think of it, we are probably doing it. And in order to get through the data, we have extremely large data sets. So for example, we have the price of stocks over the last 100 years, and there are thousands of stocks that we keep track of. So this means that our data store is about petabytes, and we do store those petabytes of data internally. And it is not only numeric data, we do have as well string data and any kind of data you can try to work out and see an edge. And our quantitative researchers use the Python tech stack, which has become the de facto standard for doing data science. So we do NumPy and we do Pandas. And Pandas will be one of the main things that we are going to talk about today. So ArcticPython is the first iteration of ArcticDB, and it has become alive due to necessity, as most good products. We had a proprietary database, which was quite expensive, but it didn't play well with Pandas. So our researchers, as I told you, they are the people who make the money. They're really good at data science. And they're really good at fiddling with data, but they don't want to try to push some data in a database which is not natively working with it. So they needed a way to push the data into that proprietary database and then read it, which become tedious. So one of those researchers grew really tired of this and created ArcticPython. The base idea of ArcticPython is to have a Pandas DataFrame, stick it somewhere into memory, and then read it. That's it. That's what people want to do. And since it was created by a researcher, not by a tech guy, it was easiest to do it on the client side. So what we had, all the operations of getting the data frame and then saving it, everything, and the compression as well was done on the machine of the one issuing the read or the write call. And then we had MongoDB storage, and the data was saved in MongoDB. And at one point, we were running the second largest proprietary MongoDB cluster in the world, and it's quite expensive. I mean, Mongo is free, but the support for Mongo is crazy expensive. I mean, it's unbelievable how much money do they want. And that's how ArcticPython was created, and it is open source as well, and you can check it at GitHub. But at some point, we decided that we can do better. Python is slow, as you might know, and Mongo has become expensive, and it became increasingly harder and harder to work with Mongo. So 2 years ago, we decided to rewrite it from scratch using C++. And the idea is the same. We needed to have simple interface. The data has to be flexible because financial data is quite non-normalized. You can have missing data, you can have data appearing and then disappearing from the stock exchanges. So we needed to work with that as well. And we needed it to fit into the Pandas data frame, into the Pandas pipeline that we have. So it had to be really easy to get a Pandas from storage and work with it and then store it again inside the storage. And ArcticDB is actually a shared library which has a Python interface. So these are the main features. I will just talk about them briefly, and then we'll get into more detail with next slides. First of all, as I said, it had to be simple. Again, it is client-based. It turns out that we don't need a database server to run all the computations. And the storage, we decided to be cloud storage. The data is immutable because you cannot break your data if you cannot change it or touch it. And this allows some nice features, which I'll talk about lately. Also, as I said, we need to be able to handle non-normalized data with columns coming into life and then disappearing, and then missing things in columns. And at some point, we found out that Pandas is slow for some things, so we had to implement them as well. And when I say simple, this is actually the most used use case of Arctic. And I will go through all the wines shortly with some analogs through SQL databases because it's really similar. So here on the first one, we create the client and we pass something which you can think about as connection string. It tells you what is the storage which will hold your data. In this case, it's LMDB, which is like hard disk storage, but it can be S3, it can be Azure. Basically, we support only that. At the next one, you create a library, and the library is something as a database in regular SQL database world. Then we create the Pandas DataFrame, which we want to stick into Arctic, and then we write it. We write it into something that we call symbol. In this case, myDF is a symbol, and a symbol is something like a table in the SQL world. And then we read it. And the most important thing is that whatever we wrote is exactly the same as whatever was read back. It is exactly the same to the byte. Talking about client interface. So the idea was that everything that has computationally done is done on the client machine. So when you want to write something, your machine would be the one which will split the data frames, as I will show you later. It will compress the data frames, and then it will issue a code to some storage. Currently, we support S3 and Azure. And one of the interesting things is that S3 is only an API. So we have both storages which implement the S3 API. These are vast and pure storages. And we do have local storage warehouse where all the data that we use is stored. And so in this way, we don't have to think about how the replication of the data is going to be handled. We leave that to the one who created the storage. And now, in my opinion, this is the most interesting part. This is the structural overview and the immutability, which I talked about. So I will restate it. You can corrupt your data if you're not allowed to change your data. And how do we do it? When you issue an update command, we will create a new version of the library of the symbol that you want to store. But we will not copy it. We will do something. You can think of it as what Git does when you are creating new commit. So we will store in a smart way only the differences between the thing that you wanted to change and the thing that was initially there. In this way, we will create a linked list of all the different versions that you have of the data. And in this way, it can grow, but at any point in time, you can get any previous version of the data that was written in Arctic. And of course, you can delete it. There is explicit delete command. And if you delete it, we can't help you. I mean, it's gone. One of the things that we had to decide how to do was how to handle the fact that S3 and Azure are actually key value storages. And the fact that the data is immutable helps us a lot, because when you create the key, we have the notion of structured keys. So the key tells you a huge amount of information about the data that is stored under that key, such as timestamp, hash of the data. I will talk about more in the next slide. But just by looking at the key of something, we already know we have large amount of information about what is the thing stored in that key. And we have two kinds of keys, like internally. One is the ref key, which is the only thing that can be changed. And we have atom keys, which hold immutable data. We never ever change the value which is held under an atom key. And here in the right, you can see the whole hierarchy of the keys that we have. A key will store either a pointer to another key or some kind of data. And at the top level is the reference layer, which is just a pointer to the latest version of the data that you have. This is an easy way to find. It. Then we have that linked list of all the versions that happened through time. And each version holds a pointer to the previous version. Then we have the index layer. These are where the B trees are created and the B trees are stored. And the B trees are used in order to get performance, to get fast searches for the data. And at the bottom level is actually the data, which is deduplicated and is also compressed. And here it's a bit more practical example of what happens during a write. First thing that we do is to compute the ref key, which is on the first line. The ref key depends only on the name of the symbol or the name of the table that you are storing. And it can be deterministically computed given that name. After that, we split the data frame. In the upper right corner is the data frame that we are trying to store. We split it, and you can see on the next picture how do we split it in this example. In real life, we would have about 100,000 rows and 127 columns in each chunk. Each of those chunks, we will compute a key, an atom key for that chunk, and that chunk will also have the index. So the index will appear in the data, and some information about the index will appear in the key. And it would have information such as the key type, which in this case is atom key, the version of the table that you're writing, the timestamp, the hash of the information, and the start and end index. For example, if you have, if your index is dates or timestamps, you would have the first and the last timestamp which appeared in that index. And each column will be compressed separately from all the columns. This is because for some columns, you can leverage the fact that, for example, you have floats or ints. You can leverage the data format, or in example, if you have floats, you know that, well, the exponent won't be changing that much, so you can leverage that fact in order to achieve better compression. At the next level, we do generate the index data segment. This is where we build the B tree, which will be used to traverse the data. And we will create another Pandas data frame holding the information for the B tree. It's really important fact in Arctic and in most databases that we do store only one type of thing. We store only Pandas data frames, and we read only Pandas data frames, and all the internal information that we have is a Pandas data frame. This is so that we don't bother with different formats of data. So we will build the B tree. We will store each of the nodes of the B tree in a Pandas data frame, create the index segment, and store it into storage. After that, when we have the index, we would create a new version for the data that you have decided to either write or update. We would generate again a key, which looks quite similar to the ugly key that we have on the fourth row. And then we'll create the ref, which, as I told you, is just a pointer to the latest data that you have saved. And this is when the write ends. And so the next thing that I wanted to talk is how dynamic Arctic is. The data frames that we work with are quite different. One of the data frames that we have has about 400,000 columns and billions of rows. But other data frames have missing columns, have randomly missing data in random rows of some columns. The other thing which stock exchanges are notoriously famous is that at some point you start getting the some column renamed. So at some point a column will appear, and we would have to do this into the data frame that was already stored. We need to be able to add additional columns, and everything that I told you is doable. We can change almost anything about the schema of the data frames that were stored into memory. And this is the query builder is something that we created because Pandas is slow. We saw that some operations such as group bys, such as filtering, are quite slow in Pandas, and for some reason they don't utilize the CPU well. So we had to do them. We have filtering. I mean, you know what filtering is. We have projections. We can, like, for example, return the sum of some columns. We can group by, which can be followed by aggregations. And this thing will only read the data that you have requested. We are not going to load the entire Pandas data frame into memory and then do the filtering, for example. We would read only the index keys that you need. Using those index keys, we will read only those data keys that you need, and we will return only those columns that you have requested. Unfortunately, we don't have spill to disk yet, but it's something that is in our roadmap, so we are going to implement it soon. And you can check out Arctic. It's on GitHub. It's open sourced. You can check us on Twitter. You can give us a star. You can raise issues. And the other product that I told you, which is supplementary to Arctic and to how we use Arctic, is Detail. And Detail is kind of an Excel for Pandas data frames. We needed a way to be able to visualize Pandas data frames, and not only data frames, but time series as well. And we needed to be able to change the values at those data frames. It can draw charts. It's basically a Python implementation of Excel for Pandas. It has everything that you'd need, and recently it got ArcticDB integration, so the things that you change would get applied to the storage. If the Pandas data frame is in memory, it would get changed. If the Pandas data frame is somewhere in storage in S3 or Azure, you can directly change it through Detail. And this is how Detail looks. It's basically a Python written project. It's running on Flask, and on top of it, I think it's React. So this was it. It was a bit faster than expected. And if you have any questions about Arctic, feel free to ask me.
So if anyone has questions, please, you can speak into the mic and just ask your questions.
Yeah, sure. We do build the data from, like, all right. Yes, we do need to iterate and take different parts of all the versions. There is no like final version, but it's fast because we don't have to iterate everything. When you have the key, it would point to the differences in the differences into the next version. So we just go and grab all the differences there are, and basically, yeah, that's yeah.
I'll ask again my question. How do you work in your team? Do you use Scrum, like sprint planning, user stories, voting stories, etc.?
It's some lightweight of Scrum. I mean, we do have a backlog, and it is shared because we struck a deal with Bloomberg recently, so we're working with Bloomberg and our team. We do have planning each week, and basically that's it. We do some fast 30-minute planning. We don't do like story points or all those other stuff that I have no idea about. You just get a task each Monday. You decide which will be the task you're working on, and then start working.
The question that I have is actually, you said that your company is it operates in multiple countries. But what does the company do in Bulgaria? What do you do in Bulgaria in comparison to the other countries for your company, for now?
Oh, we do everything. I mean, we do have researchers, so we do financial research. We have people which work on implementing the algorithms which came by the research. We have people working on Arctic. We are 3 people here in Bulgaria working on Arctic. We do have a Java team which does the actual buying of the stocks. I mean, it's integrated with the stock exchanges. Basically, everything that is done abroad is done here as well. We are not some sort of outsourcing second-hand citizens of man.
And you have some kind of collaboration between the teams cross-regional?
Yeah. We do have. Currently, we are 20 people. I mean, the office started in the pandemics, so it was kind of hard to get new people. But yeah, we fit in one room basically, so there is collaboration.
Okay, thank you.
Hello. You said that there are different versions for the data that you save. Are those different versions that you build the final data from?
Yeah. Sorry.
Are they stored on a disk on the storage, or are they just in memory?
They're stored in storage. The whole idea is that they're stored either on some cloud storage like S3 or Azure, or they can be stored in local storage if the storage implements the API that we use.
Okay, so we know that different stuff can happen with storage. Data can go haywire, or some data can go missing. What happens? Okay, the data can't get corrupted, you said that, but what happens if a single version from the data goes missing? Does that data does not get corrupted, but does it not get changed?
I see two things. First is that we leave the replication of the bytes stored to the one implementing the storage. So we don't do manual replications. We we expect, like, for example, Amazon to do it. So that's one part. The other part is, yes, you can delete some version. You can, like, for example, you can have 10 versions, and then you have decided to delete the 5th one. You can do it. We know that there are some things that are going to be used later in the chain. We deduplicate that, we store it, and you can just freely get rid of the version 5 and have your life with the next versions without losing any data. The idea is to be able to go back in time at any given point and see what data was at that given point. But deleting old data will not affect in any way the new data that you have stored later.
Okay, thanks.
Okay, I have, thank you for the presentation. I have one small question. How do you deal with the backups of the database? Do you support physical, logical, point-in-time restore?
So, backups, the ArcticDB natively, the thing that you can download from GitHub, does not do it. We have like internal workers which do all kinds of backups, but they're working currently only for man. We do have something called snapshot, which can create a snapshot of the whole database that you have and store it somewhere. And we are currently working to productionalize backup workers that can do backups to other kinds of storages from your current one, so that they can be used by the public, not only for man internally.
So you're pretty much doing a snapshot on the buckets data?
Yeah, it is kind of, I mean, not exactly. The snapshot cares about, so we're not going to rely on the API, so it's not copying the S3 bucket, because we have to work with other kind of like Azure storages. We do a snapshot of what we wrote, the bytes that we have, and just throw it somewhere.
I see. Thank you.
What queries do you run over this time series table? How do you use this database?
Okay, so honestly, the most used case is this one, where you just need to read a symbol, like on the 3rd row from down up. That's the most widely used thing. But the other thing, unfortunately, I don't have like source code here. The query builder is a Python object, and that Python object has a few like properties. Like for example, one of that property can be name of a column, and then you can do arrange as a value to that property, and it will do filtering on those things. I mean, it kind of works like what you have in SQL for selects. We do the basic select functionalities implemented with that query builder.
Yeah. But what are the business cases? I'm asking because what do you think? Do you really need all the data, and how frequent do you like use the old? How often do you check the very old transactions, for example? In terms of, I'm thinking about compressing some of the properties, or well, is it usable data what you have? How usable it is?
We do compression. I mean, if you're asking if we do compress all the data that we have, yes, it is stored in a compressed format. Currently, we're running some simple compressions such as CLZ4, but we have some other in a branch somewhere. How much do we use the data? It's used for everything. I mean, when you have some kind of trading platform, it's used to read the data while trading. It's used by the researchers to do research. And as I said, the most important thing was for a researcher to be able to get some data frame and start working with that data frame, not to waste. There are smart guys. I mean, those people have PhDs. We don't want to waste their time for fiddling with some weird databases and data formats. We want them to get the data frame and start making money.
A follow-up question about that, because you're talking about data scientists reading a lot of data, right? Like 100 gigabytes. So are we going to see a cost increase? For example, if we move from something like reading Parquet files from S3 to working directly with Arctic?
That's an interesting question. We have tried measuring Parquet files. One thing that I know for sure is that reading Parquet files from S3 is slow, is unimaginably slow. One of the researchers did a showcase of Arctic versus Parquet. Reading Parquet was about 1 hour, reading it in Arctic was about 10 seconds. So in terms of speed, huge boost. In terms of cost, I'm not sure. If I was a sales pitch guy, I would say that we do better compression and you could get smaller costs, but I haven't tested it myself.
So, if there are no more questions, can we just get one more round of applause for our presenter? This is your gift. And so, if you have more questions, the presenter is going to be in the discussion room,